So we're good.
Okay, so we said we know what a model is. We know what a linear model is. A model is just a description of the world in terms of statistical parameters. We know what a linear model is. That's a description of the world where those parameters describe a straight line. So far through 2 dimensions. What's a general linear model? Let's start by generalizing the number of variables that we measure. So let's start by generalizing spatially into the 3rd dimension. And we can do that by starting from our car. Our car is driving in Paris, and it has the trajectory of our car will form a slope on this graph. And if we know the slope, then we know how much every kilometre east will translate to, how many kilometres that will translate northwards. Okay, so we want to look at a 3rd dimension. What can we do? We can take a plane. And now we're flying out of Paris Airport, Charles de Gaulle. And our motion now has a 3rd component, and that's a vertical component. And so now we can have a trajectory or a line, not just through this 2-dimensional space that we can represent very easily on the board, but a line through 3-dimensional space that you can't represent on the board, but it's still there. So imagine that the plane flies off, and we stop it and we measure it when it gets to here, so that it's up in the air and it's moved eastward and it's moved northward. What we can do now is we can measure the slope of that motion with respect to both movement axes that we're interested in. So we want to know, we want to be able to predict the northward movement of the plane, both from its eastward movement and from its altitude movement. Okay? So in other words, we can calculate the eastward slope, and that here is just going to be the change in y again divided by the change in x. So that if we know the eastward slope, that vector of the movement, ignore the height and just focus on plane moving eastward. We know that if it's got a slope of 4, then for every unit change in the x-axis, 1 unit change on the x-axis, you'll get 4 unit change on the y-axis. And we've covered that. But the plane is also going to have a slope with respect to the altitude, or the height that the plane's flying. So let's say it's got a vertical slope, which is equal to 1. And we know that. That'll tell us that for every kilometre the plane flies up, it also goes north by 1 kilometre, because the slope's 1. Okay? So we can make inferences based on its eastward movement and on its movement in height. So all we have to do now, then, if we want to start to think about this in terms of data, is instead of having movement that's got an eastward component, a height component, and a northward component, the plane is flying through a data space where we replace east with years after university, that's one predictor. North with monthly income, that's our outcome. And the height with length of education. So that we have a years after slope, so that for every year after university, students earn, or graduates earn, 4 units more in income. And we have a length of education slope, which if it's 1 tells us that for every year you spend in university, you gain an extra unit in your income when you start. And it's when you start because here we're ignoring the other axis. Okay? Is that way of analysing the plane's movement through data okay? So we can make inferences or we can make predictions about y with respect to x and with respect now to z. So we can make predictions about monthly income with respect to how many years after university the person is currently as we measure their income and how long their education was. Okay? So here we've got a y-intercept and two slopes. Our y-intercept tells us what income is when the effect of both predictors is 0, when the length of education is 0, and the years after university is 0. So this would be for somebody who is starting in work straight away. And the length slope tells us how much income increases as the length of education increases, ignoring the other one. And the years after university slope tells us how much income increases as the number of years after you've finished your study increases per year. So again, your y-intercept, your baseline. Slope 1 tells us how much the outcome changes due to predictor 1, or as an effect of predictor 1. And slope 2 tells us how much the outcome changes due to predictor 2, or as an effect of 2. Is that okay? So we're analysing each dimension separately relative to the dimension that we were interested in. So we're treating it as two separate two-dimensional spaces. And we just write this like this now. We use the linear equation again. So if we wanted to predict score yi, so the income of a person 1 in our data set, then we can do that on the basis of knowledge of the intercept. So on the basis of our inference back to if there was no education taking place, and if the person was immediately out of what education they didn't take, basically. This is just a baseline. Plus whatever score we get here for their length of time after education times the effect of education. Plus whatever score we get here for their predictor 2, number of years they spent in university, times the effect of university, each year at university. Plus a residual error term, the leftover bits that don't fit the model. And that's it. And this time I got it right. And you standardise that in the same way. You calculate r squared in the same way, and you can have as many predictors as you want in principle. So it doesn't have to. You're not limited to a 3-dimensional space. You can go up to a 4-dimensional space with 3 predictors, or a 5-dimensional space with 4 predictors, and so on. And we can express that generally like this. Is that okay?
Can we only say, so it doesn't matter how many, no matter how many predictors, we can only say something about the outcome. Is that right?
Yes, that's what we're making inference about.
Yeah.
So you can do something tricky, which is have 2 outcomes and look at the way your predictors predict each outcome and the relationship between them, but then you're getting into multivariate statistics, and that's a different. That's a different.
Go the other way around.
Sorry.
When you have multiple predictors, there's only one way to go to the outcome. You can.
Yeah, you don't go back.
No.
Yeah. But you can look at one or more outcomes. So I'm just doing univariate statistics, and it's univariate. Might seem weird to say it's univariate statistics when we've got this many variables. We've got infinite variables over here. But when you hear someone say univariate versus multivariate statistics, what they're talking about is the outcome. So So univariate statistics deals only with the outcome. Multivariate statistics deals with multiple outcomes. So we've only got one outcome, it's univariate. So here, all of this is univariate stuff. But this generalizes also to the multivariate case. Okay? So that's multiple regression, multiple linear regression. So this is also general because it's actually the basic form of many statistical tests. Back in my day, which is surprisingly, it's getting longer ago, but it's not that long ago relative to the way we learn statistics. We did all of our statistics by hand in exercises. We didn't use computers in my introductory classes. We sort of calculated all of these sums of squareds, and we learned each test as a new thing. So here's a t-test, here's a correlation, here's an ANOVA, here's another test, and it was sort of the cookbook method of learning statistics. And it was really interesting for me to learn that all of the things that I've learned are actually small variations on this general linear model. And I can give you a demonstration of that now by showing you that a t-test is really, or can be re-expressed as a kind of general linear model. So a t-test is really just another form of regression. So all of the stuff we talked about yesterday is really just regression. Okay? So let's go back to our scenario from yesterday. And we've got this hypothesis about day shift and night shift workers at the mine and whether or not one's more stressed than the other. And we've got our null hypothesis and our alternative hypothesis expressed here with distributions. So that we're expecting that both samples come from the same population. Where what that means is that both samples follow the same distribution, which is the Platonic representation of stress at the mine, which has got a mean and a standard deviation. And that mean and that standard deviation applies equally well to both samples. And our alternative hypothesis is that the mean for the distribution that represents the night shift workers is higher because they're more stressed. So we saw yesterday that we have an independent samples t-test that we can use to test this difference, and that the numbers here represent the mean of the sample of night miners minus the mean of the sample of day miners divided by the square of the pooled variance. So this again is our punishment term. So punishment for how much variability there is in our data. And we saw that this was a test statistic where what we're interested in is the difference between the sample means divided by some estimation of how well our samples represent these two groups. And we're comfortable with that. That was sort of where we finished off yesterday. So how can we redo this as regression? Well, let's write up a regression equation. And let's now say that this data point, that's a data point for the night shift, someone in the night shift group. So that's person 1 in the night shift group. This is a data point for someone in the day shift group. This is the effective shift if the null hypothesis is true. So where there's no effective shift. This is the effect of the shift. And we're drawing our line between two places, which is day workers and night workers. And this is our error. So we've got everything we need to conduct our t-test. And this will give us an effect. This will give us a slope of this equation. And we can test then if the effect of this shift is significant. And it turns out that this slope will give us the same number as the independent samples t-test will. So the value of this slope will be the same as the t-value that we get when we conducted the t-test. It's just another way to calculate the same thing. So that all statistical methods, well, not all statistical methods, but a lot of this stuff I learned in this cookbook methodology reduced to regression. So it's very general. So rounding up and finishing everything off, let's go back to where we started. I said that this was a sort of a representation of a very scientistic model of science, of inquiry, of a way to do, very scientific way to do research, and that it was tied up to a lot of assumptions about empiricism, and that those assumptions philosophically have their flaws, but it's not too far off from what a lot of policymakers think they're doing. So let's take this framework and return back to what we were talking about in the beginning in terms of thinking of social sciences and humanities sort of on the natural sciences model and the way that policy gets implemented from these fields that we're working with. And I showed you this slide where you can go out into the world and observe that crime occurs, crime's increasing in the world, and you can form an explanation about that, which is your theoretical account, which is that crime's increasing because drug use is increasing, or drug addiction's increasing, and you can have a prediction on the basis of this explanation, which is that, well, if we have a methadone clinic somewhere, that's going to decrease crime because it's going to decrease addiction. And with that knowledge, we can go out and control the world. We can set up more methadone clinics. So this is fitting this scientific model that we started with of observation, explanation, prediction, and control. And hopefully you can see that this is actually what we're doing when we're doing linear modelling of social things. So here we have a figure. We might do a study, and we might plot the results of our study in this way, where we look at different counties or different areas in relation to how much methadone gets dispensed in those areas. Or we could increase the amount of methadone that we're dispensing in an area by setting up new clinics. We can have some sort of intervention. We can do something in the world that means that more methadone gets out there, presumably decreasing addiction. And we can also measure, say, something like burglaries per month. There's a whole bunch of research decisions that go into this. What does milligrams of methadone dispensed mean? How does that relate to addiction? Is burglaries committed really the best measure? Are there other kinds of crimes that we might be interested in? And all of that sort of thing. But let's just take this as a simplification. And let's go out and observe and collect some data points. And we observe a pattern like this. First thing we'll do as statisticians, or as sort of someone doing quantitative research who's doing linear modelling, we'll say, well, is there a pattern here? Is there a trend here? And the way we do that is to construct an explanation. And our explanation is a relatively simple one in this case. It's just a linear model. Our explanation is just increasing methadone will lead to a linear decrease in crime. So here's our model, which has just got this equation on it. Now let's make a prediction. If we set up some intervention, set up a new clinic, then the amount of methadone that's dispensed will be here. Our prediction, there's no error here, notice. This falls exactly on the line because this is not a data point yet. This is our new prediction. Then we should expect burglaries to go down to here. And this is where we're testing our theory in our intervention. And from here, we can implement policy or control and say something like, well, if this model's true and this prediction turns out to be right and we can convince people of its truth through some sort of social process, we can control the world such that we never have fewer methadone clinics or less methadone being dispensed in this amount in order to keep crime down. And that's kind of familiar, right? It's how a lot of policy debates go on. So wrapping it all up, what do we do when we formulate a research project? What do we do when we approach a research project from the perspective of statistics? Well, we start with our concept. We start with something that we can't measure. We start with something that's ineffable. We operationally define. We find a sample and an appropriate dependent variable for cashing out our operational definition in the real world. We make an inference to the population and an inference to the population at relevant times. Our concept expresses our theory, and what we want to do is have the statistical tools available to express the particular kind of theory that we want to talk about. Linear modelling gets us a long way, not all of the way. We go out and collect sample data, and we hope that we can use that to say something about reality that we don't have access to. So our theory we express as a statistical model. In this case, it's a linear model. We also saw that we can just express that with just a distribution. We can express that with many kinds of formalizations, the more you get into this sort of field. And what we're interested in doing is talking about our population statistic, as we saw yesterday. Sort of the true value that we assume to be in the world, but we really think of as some sort of Platonic idea. And all we've got to work with is our sample statistic, so we use hypothesis testing to relate these two to one another. And with the tools that you've got at the moment, your statistical model will be some variation of regression. And this is where you're able to progress with your own learning from it. And that's it for the theoretical part of the course. Thank you. So, lunch just arrived. Let's have 45 minutes and do the exercises.
Why is it called regression?
I actually don't know. It's just a word I heard in first year psych.
Yeah, it does not mean going back to